Good morning, everyone. And can you hear me well? Yeah. Okay. Good morning, everyone, and welcome to the third webinar of the webinars organized by the Kidney Care Project to celebrate the World Kidney Day. Today, we have a very interesting webinar regarding the green dialysis technologies that are going to be presented by high-level speakers on this regard. But let's wait for 5 more minutes so we give time to people to get to the webinar. So 5 more minutes and we will start with the activity. Thank you very much. Hello, everyone, and to those who has just entered this webinar, welcome. We will start in 2 more minutes. We're just giving time for the people who have registered to the webinar to access. So 2 more minutes, and we will start with this very interesting webinar. I think that we can start. So, good morning, everyone, and welcome to this third webinar organized by the partners of the Kidney Care project. Kidney Care is an EU-funded project, and I'm Cesar Crisosto, the Communication Dissemination Officer of the project. And today we are going to have a very interesting webinar, and the title of the webinar is Green Dialysis Technologies, Innovations and Practical Strategies for Sustainable Kidney Care. The speakers are very important and very key to us, to the entire consortium of the Kidney Care project. We have Karin Gerritsen from the EMC Utrecht. And then we have with her the PhD students Jan Sai and Tibo Verburg, who are going to present a very interesting data regarding what has been going on the clinical side of in Utrecht and the work being done by the Kidney Care project. So I give the floor to the speakers. Karin, the floor is yours.
Thanks a lot for the introduction, Cesar. It is an honor and a pleasure to present here something about our work on green dialysis technologies. I will just do a very brief introduction, and then I will hand over to Tibo and to Jan, because they are actually doing the real work, two talented PhD students from my group within Kidney Care. So Tibo did a thorough literature research on life cycle analyses on dialysis, and will present some of his work, and that also helps us to identify the hotspots. Subsequently, Jan will take over, and he has worked on the green dialysis technologies and will share his work. So it's a great pleasure that they are willing to do that. Jan, can you share the presentation? Next slide. So yeah, our work is a bit in line with the Green Deal, the European Green Deal, and it's of course becoming more and more important now also with the current energy crisis. Next slide. And perhaps nice to mention that within the Netherlands we have a Green Deal on sustainable healthcare with actually comparable aims. So also we aim for climate neutrality by 2050. And since within healthcare we have a dual responsibility, so we need to deliver high quality patient care, but also do it in a sustainable way. And that's primarily important for kidney care since, next slide. As you all know, the footprint of dialysis is extremely high, much higher than that of an average patient. And here the data from Utrecht. So we consume an enormous amount of electricity, water, and generate a lot of waste and require a lot of transplantation. So it's a real challenge to do this in a more sustainable way. We need to rethink and redesign dialysis. Next slide. But of course, the first aim is to prevent dialysis. So promote healthy lifestyles. And the Spanish group, one of the other talented PhD researchers, next click, Jan, has shown that, albuminuria screening can also really have a big impact, ongoing impact on the emissions of kidney care on the long term. When you incorporate such a screening program, albuminuria screening program within your country. And subsequently, it's when patients have CKD, it's very important to initiate drugs timely, like the new SGLT2 inhibitors, GLP-1 agonists. Then subsequently timely referral to a nephrologist. And within your nephrology department, it's important to have a well-functioning living donor program. So aiming for preemptive transplantation, since as Tibo will show, the emissions of transplantation are much lower than that of dialysis. Consider conservative care for the old frailty patients, where research has shown that Dialysis not always improves quality or duration of life. And then when you have to do dialysis, consider to do incremental dialysis when patients have considerable residual kidney function. But when you have to do dialysis, we should do it in a green way. So I now will hand over to Tibo, who will first present on his work on his literature search on life cycle analyses, identifying hotspots, and subsequently Jan will take over. Go ahead, Tibo.
Yes, thank you, Karin. Like you mentioned, I've been working on a review of life cycle assessments of kidney care, and it's one of the goals of the Kidney Care Consortium to do a lot of these new life cycle assessments to see both what is the impact of the treatment and how can we reduce the treatment and how big would the impact be of those reductions. So these are a few examples of some of the studies that have been done, but I will take you on a journey both through studies that have been published that I am reviewing and on some of our own studies from Kidney Care. So could you go to the next slide, Jan? So one of the things to note, like Karin just mentioned, there's a difference between how we treat the kidneys and what is the impact on the environment. So especially disease progression, like you can see stage 1, 2, 3, 4, and then towards 5, it becomes more and more environmental impact. This is in carbon emissions, but the other impacts are comparable, that it increases upon a later stage of the disease. And then peritoneal dialysis has a relatively high impact, but hemodialysis has the highest impact, but then transplant and supportive care have a lower impact. And what's interesting to note, the impact of hemodialysis is around 5 tons of CO2 equivalent per patient per year, which is actually close to the global average CO2 equivalent footprint. So a person on dialysis might have a double the impact of an average person in the world, or it's also equivalent to about 50 hours by airplane. So just to give a little bit of a context, could you go to the next slide, please? However, in the literature, there is quite a high variance between life cycle assessments. So as you can see on the right, between 3.8 and 10.2, there's quite a high variance, and this is caused by a bunch of different factors. One of the things is that some studies set different boundaries. So whether you include something in the study or some things you don't include, such as, for instance, the heating and the lighting of the center, that might increase the CO2 emissions. But there's also different methods of obtaining data. So if you might look at the electricity use of the HD machine, you could look at the device specifications, but you could also measure it directly at the machine. Or you could look at the entire department and see what is the electricity use. And the way of obtaining this data can then change the results of these studies. But there's also, of course, local differences. So whether you measure this in a country where all the electricity in the grid is made with coal, then you get a very high carbon intensity and therefore high carbon emissions. But when this electricity is made with solar or other renewable energies, then you get a lower carbon intensity and therefore lower carbon emissions. But other things that might influence are travel distance. That's of course understandable. The water availability in that location. How the waste is disposed. Recycling might have lower emissions than incineration. But also sustainability interventions, which we will talk about a bit later in this webinar. Good to note is that our own study showed around 4.4 tons of CO2 equivalent per patient per year, and previously I showed one with around 5. So it will be approximately around this range. Yeah, between 4 or 5, maybe a bit higher, like you can see from the range up there. But I think it's not really relevant to know the exact impact. Like I say, it can differ between locations, but the main thing is that we can reduce the environmental impact. So these life cycle assessments, they can give us an indication of the approximate impact, but then mainly what are the hotspots where we can reduce the impact. So could you go to the next slide, please? So let's look at what are these main contributing factors. Like you can see in the graph on the top right, the main factors are electricity, the production, transport, and waste processing of consumables, and then travel. And especially those last two, the consumables and the travel, have a high impact on CO2. And I do want to mention also one other thing, which is pharmaceuticals. This is not mentioned in every study, but this actually, in the few studies that have studied this is quite a high impact category. So it's also definitely something to consider. And on the bottom right, you can see one of our own studies. I'm sorry for the low resolution here, but what we show is what are the different consumables and what is their impact individually. So as you can see, there's two on the left that have really the highest impact compared to all the others, and that is the dialyzer and the bicarbonate cartridge. So these are definite hotspots that we can focus on, that we know these have the highest impact. So that's where we can potentially find reductions by finding more sustainable alternatives or way of using them. And one last thing that I want to mention there as well is that all the things I've just shown is in CO2 equivalent emissions. But of course, we have also a very high water use, and we have other impact categories such as ecotoxicity for pharmaceuticals, or a bunch of different impact categories. But just to keep it simple, I just focused on CO2 emissions right now. Could you go to the next slide, Jan? So like I mentioned, there's a few high impact categories within the treatment, and we will focus on a few of those in order. So I will start by focusing on transport. Could you go 2 slides forward, Jan? And transport is, like I just showed, is actually one of the really big impact categories. And it is definitely part of the treatment because these patients have to travel a lot. So one of the things that can be done to reduce this, like you can see on the right, is to use home hemodialysis, because then, of course, the patient travel is negligible. However, it should be noted that if you then use a home hemodialysis regimen where you have a higher frequency or longer duration of treatment, then it might actually negatively influence that gain in emissions. So that's definitely something to consider, but at least then you have not the emissions from the patient travel. Another option is microclinics that are close to the patient's home. This is one of the things you can do that both improve the sustainability and also improve it for the patients themselves, because they won't spend as much time having to travel. So Dianet in the Netherlands is a good example, which has kind of microclinics closer to the patient's home, which leads to better treatment and sustainability gains. And we're actually doing a life cycle assessment also on microclinics and their impact, so that will soon be published. But other options is, of course, carpooling with different patients or public transport. These are options that can always be considered in collaboration with the patients. And currently there are, of course, a lot of things, or also in the previous years, of new home hemodialysis devices that might definitely improve patient care. And we are also looking into what is their environmental impact. So we're currently doing life cycle assessments of Next Kidney, Visidia, and Next Stage machines. And actually at the ERA Congress, we will present some first results from this life cycle assessments on these. But these are all options to reduce the impact of transport, and I will hand it now to Jan.
Okay, now I'll continue on the other aspects. So first we'll see some of the technologies we do to reduce water consumption. And yeah, we start from reducing rejection water from the reverse osmosis machine, and also reducing some of the wastewater produced when using the purified water. And one thing we can do is, of course, to recirculate reject water and use ultra pure water. So this is the flow diagram of our machine, RO machine in UMC Utrecht. And as you can see, unused ultra pure water and reject water are recirculated into the RO machine. So it's not just waste. And so we use a relatively new machine, which is installed quite recent years. And we have a concentration factor of around 66% of recovery. And we are also doing water measurements on the RO machine, just to understand what kind of consumption we are having in the hospital. And we use a technique called ultrasonic sensors, and we attach it for 1 week in the pipeline, and we get graphs as shown in the right, and we know in what time what exactly the consumption is. So in the upper graph you see the consumption in the distribution ring, and below is the reject water. So gives us a quite clear idea of how much water is consumed and also rejected in different times, and when the RO is disinfecting, when it's and the distribution ring is also disinfecting, and also during the treatment sessions. So what we have measured in 1 week, our ward, which is relatively small, in UMC Utrecht, we have around 18 beds with 60 patients a week. So we already consumed almost 50,000 liters of water, and for an average per treatment, around 350 liters are consumed. And actually, although the settings of our RO machine show we set it into 66% recovery, actually only 53% of the water is used, because there's also additional water used for disinfection and things like that. And we also try to measure energy consumption. So we also installed power meters on the power lines, and we measure and we get energy consumption readings from the RO motor and also the disinfection heating unit separately. And you can see graphs at the right. These are how much power is consumed during disinfection and also in different sessions. So, for example, in Saturday we only have half-day sessions. So at the first half at the morning, it's more power it's consumed. But in the afternoon, we can also see that although there are no patients, but we still turn the RO machine on. So, but still, it's consuming a lot of power. So that's one thing that can be improved. And in the disinfection unit, we see that in the morning, where disinfection is happening, a lot of heating of the water is done. So there's also quite a lot of consumption of energy. So in a total of a week, we consume 1,510 kilowatt hour of energy, and around for each treatment we have like 11 kilowatt hour of energy consumed. And for the RO system, 61% of those are from the RO system and 39% from dialysis treatment. So we have a plan of optimizing the use of our RO machine. So first, we can increase our concentration factor. As I mentioned, the settings right now is 66%, but from the user manual and recommendation specifications of the RO machine, it can actually achieve 80% and above of a recovery rate. So we can change that. And considering the water in Netherlands is quite clean, so the conductivity now we get from the pure water is quite low. So we definitely have a room to increase the concentration factor. So theoretically, now 66%, we can increase it into 80%. And from the guidelines of the Dutch nephrology, 1 to 10% micro Siemens per cm of conductivity is allowed. So that also shows we have quite clean water compared to other regions of Europe. And another plan is also to shut down the RO treatment in off-clinic hours, because although no water is consumed during that time, but still the RO machine is on, and it's continuously recirculating and producing clean water. So as you can see at the graph below, the consumption. So at Sunday and Saturday, we usually have half-day clinics, and the water from the treatment, there's more reject water from the treatment because a lot of the water is not used and just rejected. So yeah.
We already incorporated this, Jan? So but we still have to do the measurements, what the results are.
Yeah. So
Yeah.
the optimization plan is now underway, but we still have to measure how much how much energy and water is actually saved from what we have incorporated. And
Because the measurement is quite challenging, because
yeah,
we have
yeah,
to install flow measures and so meters, flow meters
yes,
and energy
yes.
meters. So it's quite complex and
And
yeah,
we
still need
also
to do
can
that.
reduce disinfection frequency. So although we're not gonna implement this, but this is also one possibility. So now in UMC Utrecht, we actually disinfect every day, but we know some clinics, they only disinfect 3 times a day. And we, and also in the guidelines, it's said that there at least it can we only need to disinfect after 72 hours. So there is we don't need to actually disinfect every day. So that's one also possibility. So now as you can see, it's every day, but we can actually plan just 3 times per day per week for the RO disinfection and ring disinfection. So, but we also know that disinfecting the ring or disinfection is quite important for the RO treatment plant because it guarantees clean water and no contamination on the distribution of the water. So we also had discussed that if we are to do this, we need a validation plan and we have to reduce the disinfection frequency step by step. So this is just a table showing how our plan could be. So we measure them we reduce one time measurement. So we have we do it every day and we reduce them one day by day and we measure them as we reduce the frequency. So now, but we can also reduce permeate production. So our machine now, it's the permit in the specifications, it's actually used to produce more than 1,600 liters per hour. That's the capacity now, but from our measurements, we know that actually only 800 liters per hour is used from what we consumed in the ward. So this capacity is actually too big for a ward. But and um, and another recommendation maybe in the future is to also install the newest machines. For example, in Aquabos, B Brown, they also have newer machines. So our machine is relatively new, which recirculates already unused produced all pure water, but the newest machines they can even adjust the flow permit production and even recover energy loss from pumps. So they I think they also can adjust A0 value, so they have an automated disinfection program, which you don't for our in UMC Utrecht now we have a fixed disinfection rate, but in the newest machines they can adjust and set its A0 value and it disinfects according to that, so you don't have excess heat and water used during disinfection. So the newest machines now actually have already incorporated a lot of new technologies which can further reduce energy and water consumption. And now in UMC Utrecht, we also recently just um, we recently just accepted an investment to install new monitoring sensors, which is also a nice progress from the research because we found that actually measuring and monitoring the energy and water consumption in the ward gives us a lot of information. So now we also are planning to install these monitoring sensors from Green Tech. So they are able to we can be able to see water and energy and heating consumption, usage of energy, and etc. A lot of information will be able to be shown real time in the future in UMC Utrecht. So this is some of the user interface of the system that we will be installing in the future. Of course, we can improve the efficiency of reverse osmosis, but we can also try to decrease what we consume in the ward. And first, we can one way is of course to reduce dialysate flow, but that would require careful prescription from the nephrologist. And there's also new functionality in the new machines, which is EcoFlow. So instead, the machine have a setting that they adjust the dialysate flow. So it doesn't use that excess flow for doing dialysis. And another thing is that you can turn off the machine after priming. What people usually do in the ward is after priming, they let the machine go standby, and in standby it actually still consumes a lot of dialysate, and maybe the patient come maybe 30 minutes later, 1 hour later, and then it starts dialysis. So, but during that time when the machine is waiting, it still consumes a lot of dialysate. So by turning off the machine after priming, it actually saves some dialysate consumption. And there are also other devices, new devices, regenerative dialysis devices, which are also mentioned in Tibo, like some home devices like Next Kidney, which we are also doing a trial here in Utrecht. So these kind of devices, they don't use single pass dialysate, which means the dialysate is only used once, passed through once in the field, in the dialyzer, and then thrown away. But in such devices, it's actually, they use a sorbent, which you see in the cartridge here. So the dialysate is recirculated into the sorbent, cleaning the dialysate, and then recirculating it back to the dialyzer. So a lot much less dialysate fluid is used in such devices. Yeah. So here, this is a schematic of what is done. So in the dialysate circuit, there's a purification unit, which is the sorbent that constantly regenerates the dialysate. So in per treatment, only 4.5 liters of dialysate is used, compared to in HD machines, more than 150 liters is used per session. And we're also doing an LCA on this machine because we also have additional components such as the sorbent. So we actually want to benchmark and compare whether it is more sustainable or how much more sustainable these kind of machines are. So we're currently doing an LCA, and hopefully will have some results in the near future. And we proceed to energy. So energy, we can also preheat dialysate with renewable energies. From the same company, GreenTech, they also offer other solutions. For example, they have a hero system, which integrates renewable energy, such as solar or geothermal, into the RO system, water treatment system of the ward. So it preheats RO water before it goes to the dialysis machines. So usually uh, water from the dialysis RO machines are cold, and it's heated to body blood temperature, which is around 37 degrees. But here in this system, we can use renewable energy to preheat those water, so that not lesser heating is used in the dialysis machines, and also for disinfection. So by that, we can reduce the CO2 emissions. And there's also another technology we are currently investigating, is forward osmosis. So now with reverse osmosis, pure water is produced, and we we dilute the concentrates and make dialysate fluid. But there's another way of producing dialysate actually with forward osmosis membranes. For here, as you can see here in the left, reverse osmosis uses a lot of pressure to generate pure water. 10 bars in the context of dialysis wards. And forward osmosis, only less than 0.5 bar is needed. So they use a natural process which water goes through the membrane because of osmotic pressure difference. And in the right is the schematic of the process. So an RO-based preparation, pure water is generated, and then the acid concentrate and bicarbonate concentrate is diluted with pure water and becomes dialysate and used by the patient. But in of FO based, forward osmosis based, we can directly produce dialysate with the FO membrane. So tap water, so we no longer need to produce pure water. We can just use tap water, and it passes through one side of the FO module, and then the other side is acid concentrate, which is more concentrated, so it naturally um, uh, attracts water from the tap water and dilutes the acid concentrate, and then it can be directly used after adding bicarbonate to the dialysis fluid. And this is how the process is looks like in our simulations. So it starts with high concentration of dialysis concentrate, so 45 times more concentrated, which is the original concentration of the concentrate. And then it dilutes gradually until the end, which is used dilutes gradually when it's when it's at the end of the module, and then it can be used by the patient. So our calculations show that only 3.5 energy is consumed compared to RO-based preparation of energy, and with the Dutch water conditions, up to 90% of water recovery can be achieved. And we can proceed to waste. So one first recommendation of waste is, of course, to investigate your waste streams. So this is the waste produced by the ward in one day in UMC Utrecht. As I just mentioned, UMC Utrecht is a small ward compared already, but as you can see, still a lot of different kind of waste and a lot of volume and weight of waste is produced. And one technology that can be implemented is to disinfect these waste, biohazard waste, and into municipal waste. And after disinfection, it either can be disposed as just general waste, or it also opens some possibilities of recycling. So in UMC Utrecht, we are also working with a company, Blue to Green, which provides solutions for recycling biohazard waste. So a lot of waste actually in the ward is unrecyclable because it's contaminated with blood. For example, the dialyzers, the blood lines. So a lot of the waste is actually, but it is also very nice plastic. So, but first you have to disinfect that. And we can also use a central acid delivery system, which we did an LCA last year, and we compared the how much carbon footprint is reduced from using this kind of system. So in UMC Utrecht, we use Ecomix from B Brown, but Fresenius also has their own system, and we compared. So comparing to using canisters, liquid canisters, 58% of carbon emission is reduced because of lesser transport. So in this kind of system, instead of transporting liquid, now dry powder is transported to the hospital, and we have this big system that is installed in the ward, and it dissolves the powder and makes it into a big acid and makes it into acid concentrates and store them into these tanks. So no longer so one barrel is of 200 kilograms of powder is transported, and it can produce almost 200 liters of concentrates, which can be used in a lot of patients. So that's one reason. So you can see one reason why lesser carbon emission is used, but also because of packaging. So in the canisters, we used to have individual canisters used for each patient. So barrels of acid concentrates using a lot of plastic, but now one big barrel of dry powder is used. And also these barrels are actually recirculated between B Brown, so we don't throw them away after one use. B Brown actually collects them and then fills them with new powder and then send them back to UMC Utrecht. So this saves a lot of plastics used for acid concentrates. But how about bicarbonate cartridge? So as you may know, to make dialysis fluid, acid and bicarbonate is used together to formulate the final dialysate. So we only have the central acid delivery system, but how about the bicarbonates? We still use individual bicarbonate cartridge for each patient. And in a waste audit, you can see 150 cartridges are used per week, and we found around almost 50% of the bicarbonate powder is unused. So you can see these are all waste used cartridge, but you can see a lot of powder is left inside. So not everything in the in the in what's shipped to the UMC is used. And so we're also trying to design a reusable bicarbonate cartridge. So in the left, you can see the 10 R's, so different R strategies to reduce carbon emissions. And one of them is trying to reuse the cartridge. But as you know, these cartridges are single use. But one idea is actually to design something that can be reused. So we have this exercise to design a reusable bicarbonate cartridge, which can be refilled and with new bicarbonate and then used by the ward, and also adjust the bicarbonate powder volume. And in the left here, you can see this is an LCA we did on the single-use bicarbonate. So although there's also a lot of carbon emissions come from the plastic, but actually more of them comes from the sodium bicarbonate, which is the chemical powder inside of the bicarbonate cartridge. And in the waste audit, we almost 50% of those is unused. So it's very wasteful of that. So in the new design, we try to reduce single-use packaging, and we also can adjust the powder volume inside these to make it more tailored to the ward. So here in the right, you can see a comparison of the single-use and reusable bicart we designed. So although after 2 times use, the bicare, which is the new design, still has more carbon emissions because of the bigger emission we need to produce these kind of products, and the plastics used, and it's more complicated, more components. But after 10 times used, already 33% of the carbon emissions can be reduced. Although every time it's reused, we need to sterilize it, we need to wash it, so there's an additional carbon emission used for cleaning. But if you look at the long term, after 10 times use, already 33% is reduced, and after more times, even almost 50% can be reduced. So that is one way, but we also know this way is the long path. So we need to design the product, we need to produce the product, we also need to get certifications of this product. But we also know that there are some solutions available in the market. But unfortunately for UMC Utrecht, these are not yet available. So, but we know such technologies exist. For example, the central dialysis fluid delivery system, which is very common in Asia. For example, Japan, Korea, China, they all use these kind of systems. So it's very similar to the acid central delivery system, but instead of just the acid, they also have the bicarbonate part. So in the schematic here shows they have the powder, which is mixed in the mixer, AB, the acid part and the bicarbonate part, and they have a supplier AB also, and it supplies to all the dialysis machines individually, which they formulated in the dialysis machines. So they have this system, but we know it's more technically challenging because bicarbonate is more unstable compared to acids. That's why it's more difficult to implement. But in Asia, they already have this technology that which is used for already several decades. And first of all, this is very labor saving, so you don't need to deal with the acid, you don't need to deal with bicarbonate. It's very simple, pleasant, and very cost effective. Maybe one downside of this is you cannot there is a limited type of formulation you can use. So in this, you only have one type of acid and one type of bicarbonate. And if you want to use more, you need more tanks. And we
But there
also
were
know,
centers in Thailand, there were centers in
yeah,
Thailand and China that also have a separate bicarbonate, separate acid,
yeah,
so that you can fine tune. Yeah.
yes. And of course, the last, the most minimum thing we can do to reduce carbon emissions is to recycle, right? But for the bicarbonate, for example, in the bicarbonate cartridge, as you can see, we cannot really separate these. So now it still goes to the general waste because the plastics and the powder is together. We cannot separate them because this is hard plastic. It's very difficult to open. Um, but actually the plastics is very nice plastics. It's PP, and inside the powder is soda powder, which is very clean, medical grade, and it's not contaminated, but it's a lot of waste just to throw it. But in B Brown, we know in Germany they actually have a program of collecting and separating and recycle their own products. So in their own clinics, they collect all used bicarbonate cartridge, and they collect it to their manufacturing site. They break the containers, they separate the plastics and the powder, and they have a way of recycling them. They have partners that recycles the plastics and also the powder inside. But unfortunately, it's only in Germany because of course it's very difficult to transport waste across the border. So, but probably in the future, this could also be possible. And we have talked about acids and the bicarbonate consumables. Now we also can talk about the dialyzers. So also one of these dialyzers are used for each patient. And we are now also investigating on reprocessing these single-use devices. Uh, Historically, like 20 years ago, actually a lot of these dialyzers are reprocessed, but because of rise of labor costs and also reduced costs for such dialyzers, lesser and lesser people are reprocessing them. But recently in the MDR in Europe, we also see new opportunities. In 2017, the MDR, which is the recent amendment of the MDR, they have an Article 17, which describes the reprocessing of single-use device. And there's also a new regulation, which is implemented in 2020, specifying how the reprocessing of single-use devices. So the common specifications are reprocessing. And this is the high-level regulation for reprocessing here in Europe. But also there are new laws and national laws that further provides opportunities. So normally, if you want to reprocess a single-use device, you have to relabel it as a new device. So you have to act like a manufacturer. You have to do the validation, verification, and you need to find a notified body and do the CE marking again for the reprocessed device. But now national laws allows something else. So there are derogation rules. So Article 17.3 and Article 17, paragraph 4. So these two are different rules. So aside from manufacturer obligations, and some countries in Europe actually allows that. So you need national regulations for this to happen. So in Article 17, paragraph 3, you can actually follow if for example, a hospital, they want to reprocess single-use devices, they can do it their own. So they don't need to act like a manufacturer which has a lot of rules. So this is also specified in the common specifications. And Article 17, paragraph 4, this also allows hospitals to outsource the single-use devices they want to reprocess and use it in the hospital in the condition that it's only used in the same hospital. So this gives a lot of opportunities. And in January 2025 in Netherlands, we have passed national laws allowing these to happen. And so a lot of people, I think, in the Netherlands is also trying to explore possibilities of doing this here. So also in our lab, we are exploring reprocessing of dialyzers. So we have this machine in our lab installed. Just recently, we're working with a company in US. So this machine is FDA certified, not CE certified, but it is FDA certified, which can be used in US, but not yet in Europe. So we have this machine installed in our lab to do experiments. And of course, we know the challenges is very clear, the labor cost. That's why, although it's certified already in US, it's lesser and lesser people wants to use such devices. So we have this installed in the lab to do experiments to test whether it's also applicable to dialyzers used in Europe more. So different dialyzers are used in Europe and US, but we also are testing this device and exploring next generations of such devices. So we know that technology exists, but we need to improve the design or even include automation to make these more suitable for the use in Europe. And Kidney Care also has Abbas and Hafsa, also our colleagues, brilliant colleagues. They also did LCAs on this device. So if you compare one dialysis session without clear flux, so single use, and if you reprocess the the dialyzer and the carbon emission of that, and you can see there's a big difference on almost 70% reduction of the global warming potential and 77% of water use, and also energy use and reduction of ecotoxicity. So I think this is my part, and I'll hand it back to Karin to wrap the presentation.
Thanks a lot, Jan and Tibo. Yeah, just to conclude, I just want to mention that within the Netherlands, we have a very large initiative ongoing, a roadmap towards kidney replacement therapy, better kidney replacement therapy. It's a large ecosystem funded by the government and led by the Dutch Kidney Foundation, where we work towards better dialysis, but also we intend to make it more sustainable with a kind of a final goal to work towards implantable bioartificial kidney as the most sustainable option to make dialysis obsolete. But that's something for the far future. So with that, I would like to conclude this presentation. Thanks a lot for Thanks a lot for your attention, and we would be happy to answer any questions.
Thank you. Thank you very much to the three of you. Thank you very much for the interesting work that you're carrying and on especially on EMC Utrecht. I have some questions from the Q&A section that we have here in the platform. The first one says that it's asking how many liters of water are used to generate 1 liter of dialysate.
Maybe I can answer that. Yep. So
but I think it's for they mentioned the regeneration of dialysate with the small machine, isn't it? Next kidney machine. Do they is that the question?
I think that it was done at the beginning of the presentation when you were presenting the general numbers of the general numbers.
Yeah.
So,
but the question is about regeneration of dialysate.
Mm-hmm.
Is it about the next kidney system? Because there we do 36 liters for 2-hour session, and we only use 4.5 liters of dialysate. We do a flow of 300 ml per minute, dialysate flow, and 2-hour treatments. That's the modality that we're currently testing in the clinical trial. And Next Kidney is working on cartridges also for longer dialysis sessions, so also for 4 hours and for nocturnal dialysis. But they apply a dialysate flow of 300 ml per minute.
Yeah.
And also, it's completely regenerated, so there are no toxins anymore in the dialysate, only for the middle molecules. At the end, there's a little bit of saturation, but it's still better than a convention. For example, treatment with next stage at 200 ml per minute. Then it still performs at least comparable with regard to also clearance of middle molecules. I don't know whether that was the question, but so we do 36 liters of dialysate with only 4.5 liters.
Yeah, but for it's asking about the HT for one dialysate concentrate, we need around 44 liters of pure water to dilute that, and to make this 44 liters of pure water, if you look at our what we have measured in the ward, the RO machine, it only have an efficiency of around 50%. So you have 2 times of that, so maybe 80 or 90 liters of water to make one to dilute 1 liter of concentrate, and that becomes 90 liters of dialysate. Yeah,
that's before we implemented all the changes, but now we've implemented lots, but we still need to do the measurement because
it's an ongoing work. The things that there are many things that I wanted to discuss with you because there are very important things that I wanted to ask you. Like, for example, it was amazing the part that you were talking about the green tech dialysis monitoring. It was really interesting, and for me, it's going to be very interesting for the project because I wish to know how this is going to fit the benchmarking tool that is being developed for the kidney care project.
Yeah, we did not discuss that yet, but that's a very good idea. So we just got the approval by our department that we can purchase this. So they will fund it. And we still need to install it, but then it would be very interesting to perhaps use it for the benchmarking tool. Yes, that's a very good suggestion.
I think it's that for the people who doesn't know, for the kidney care project, we implemented a benchmarking tool with data is going to be available also for people interested in applying also the optimizations inside of the clinical site. So it's a great opportunity. We have also, if you go to kidneycare.eu, you can also go to the call for applications to become a kidney care associate pilot site. And if you're also interested in knowing a little bit more regarding kidney care sustainability, also we have training modules that have been developed by our partners. In the meantime, I want to thank our speakers. And thank you also, as part of the consortium, very much for the work that you're doing, for the terrific information that you're providing. And also, as one of the participants to the webinar has said, just like the CO2 production in PT and HD are incredible, but that's the awareness that you're also doing through the investigation that you're doing inside of the clinical side. So thank you very much for that, because our responsibility as a EU project of EU funded projects are also to get a little more information of and opening the eyes of the people regarding these matters. I wanted to remind the participants that we have 2 more webinars to go, the ones that have been organized by the Kidney Care partners. We have one tomorrow regarding sustainable kidney care, listening to patients in times of climate change. And then we have another one on the 23rd of March, that is Teach Yourself Sustainable Kidney Care, where the learning course is going to be showcased to anyone who is interested. So Karin, John, and Thibaut, thank you very much for being here. Thank you very much for the presentation, and have a nice day.
Thanks a lot.
Thank you too.
Bye.
Bye-bye.